WOLOTYRA.
Wait, Wol. Oh yeah.
Wolo
That's
Tyra.
wall.
Tyra.
WAL.
Engine Solier is not installed.
Okay, so from yesterday we learned. So we'll review a little bit for the benefit of people that were gone, right? So if we wanted to do something like, for example,
Wait, you were gone, weren't you?
no,
You skipped out on the track meet?
Yes.
no, I was there for the track meet, but I didn't have to go. I was able to be here for this class. I didn't leave as early as you
Yeah,
guys.
because the running events don't start till
So
Were you here for physics?
we did some stuff. If we go back, no, I was gone for physics.
Oh, so we didn't do anything yesterday in physics then.
No,
Okay,
physics
we're
are
good
fun.
then.
Physics
We're
are
only
fun.
one
Yeah.
class more. Cool.
Okay, so if we go back here, this is where we left off a couple days ago, right? Looking at, or no, hold it, no, definitely not.
You're in the middle of some problem.
What?
Oh, no, so we did that yesterday.
Was that a double absolute value sign?
No, you'll see.
No, we did that already.
Yeah, we're here. We're here.
Okay, this is right. This is where we were, right? So we said, let's just review. We said 2 days ago, right? We were talking about how we could do a finite sum, meaning we could estimate the area under a curve by using rectangles, right? But then if we wanted to get an exact answer, what do we do to the finite sum?
It as n approaches infinity.
Good. Okay, we're going to let the number of rectangles go to infinity, and then the upper and lower sums would converge on the exact answer, right? And so being as we're going to converge on the exact answer, why not pick the easier of the two, right? Which would be the right limit, where we can use a plus I delta x instead of a plus I minus 1 delta x. So we'll use x sub I instead of x sub I minus 1 to define the height of the rectangle, right? Is that all? We're good with all that?
Yeah.
Okay. So if we're good with all that, then that got us to the point where we could do something like, for example, we could find the area under the curve x squared from 0 to 2, right? Exactly by letting the number of rectangles go to infinity. Well, if the number of rectangles we're going to call is n, right? Then if we're going to pick uniformly wide rectangles, then delta x would just be the width of the interval divided by the number of rectangles, right? So 2 over n. And we end up with a would be 0, delta x is 2 over n. And so x sub I would just become 0 plus I times 2 over n is our delta x. Or in other words, just 2i over n, right? So for our specific function, then x squared, we would get the sum of f of 2i over n is just 2i over n squared times delta x. But the delta x is a constant insofar as the sigma is concerned, right? It's a constant of the sum. It's going to be a constant factor. So because it has no i's in the expression, we can pull it out front as a constant factor. We're good? Right? And then we had to take care of this guy, though, right? We had to take care of what is the sum of 2i over n quantity squared as I runs from 1 to n. And so that's the part where we'd have to invoke these summation rules, right? And these are just, it's not like I didn't take the time to write these for you in class or let you guys figure these out. I just don't want to take that time. But they're in the book, no big deal. So the sum of I squared as I goes from 1 to n is just this every time. It's just going to be the expression n times the quantity n plus 1 times the quantity 2n plus 1 over 6. So if n were 200, that would be 200 times 201 times 401, all divided by 6. This would be my answer, okay? And it'll work out to be an integer, of course. If we use this rule, then look what we can do, right? We can take the 4 over n outside of the summation, and we end up with 8 over n cubed, and then we've just got the sum of I squared, which is that, right? So we end up with now, we've taken the sum, and now we've got this big expression in terms of n's, right? Well, we're now going to get to the point where we can take the limit, right? We could pick any number. By the way, this is kind of cool, and I didn't mention this. At this point, we've got a sum as a function of n, don't we? right? So we could even write this as, this is really something like, we could call this area as a function of n equals that. And now we could decide, that n's a parameter, so we could let the number of rectangles be controlled. We could say 10 rectangles. If we want to choose 10 rectangles, then this finite sum is going to give us that answer when we evaluate at n equals 10, right? You see what I'm saying? So we could actually just, we could look at those individually and watch the a sub n converge on the right answer as n gets bigger. But we've sort of seen that graphically. And so if we just now take the limit as n goes to infinity, well, this is what we get, right? What we saw happen when we simplify, we end up with this sum of these three terms. We're taking the limit of this sum of three terms, and then as n goes to infinity, both of these second and third terms get extinguished because they've got powers of n in the denominator, right? So the denominators explode, the fractions go to 0, and we just end up with only 8/3, which is the right answer, right? We saw that graphically. It was 2 2/3, okay? Yeah, a lot of stuff, right? So we did that. Well, yesterday we went one small step further with that, and we said, okay, we could take this process and generalize it. We could call this a Riemann sum. And really all we did was we said, okay, well, to make this completely general, being as we know that we know that if the number of intervals is going to 0, or going to infinity, sorry, it doesn't really matter where we choose to define the height of the function on the ith interval. If we go back to this picture, for example, oh, where's my picture? Like right there, for example, if this is the ith subinterval, well, we could use the right edge or the left edge or somewhere in between if we want to. As that interval shrinks to 0, it's going to match the curve perfectly anyway, right? So in our Riemann sum, we define there we go. We define C sub I to mean any place, any x value on the ith interval. Doesn't matter, right? I always think of C as representing the most convenient place, which will always be the right edge. Okay. So we could always, and we'll get to that in a second. So we can sort of let this collapse into a more convenient form for us whenever we want to. But this is totally general. Could be any place on the ith subinterval. We even say delta x could be indexed. The width of each interval could vary, right? It doesn't have to be uniform. It could vary. And in some cases, that makes sense algebraically to do that. I don't care if you're experts doing this because you're never going to do it, right? This is not the way you're ever going to take an integral. And so I'm not going to give you a bunch of bizarre area functions where you've got to figure out what the indexed value of delta x sub I should be, because nobody does that. I mean, it's not anything, it's not important. But we have that freedom now, right? We still know that the exact area, right, the exact area based on a Riemann sum is going to be the limit of this sum as the norm goes to 0, right? If we don't, and what that means is, it's just a notational thing, and all it means is, if we don't have uniformly wide delta x's, if the widest one, the biggest one, goes to 0, then that's going to push all the other ones to 0 also, right? So that's all that stuff means. This is the way you're going to see it in a textbook, for example. But in almost every case, what we're just going to choose to say is, well, okay, well, let's not index these. Let's let delta x sub I just equal b minus a over n. Let them all be the same, right? And if delta x is b minus a over n, then letting the norm go to 0 is equivalent to saying let n go to infinity, right? Because then all of those subintervals are going to 0 at the same time, in the same rate, right? Let's choose the most convenient place to calculate the height of the ith rectangle to just be the right edge, x sub I. Okay, so we can always just do this exactly the way we just did, right? We can do it this way, right here, but that's just one option that's available to us in the generalized form of a Riemann sum, right? That's all we really talked about there. But then we did the really cool stuff. Then we said, okay, let's take the function f of x equals x, and let's see if we can coax out a pattern, right? We were able to calculate the area. This is a geometric area, right? It's a trapezoid. And so we're able to just find, with pre-calculus stuff, we can find the area pretty simply. It's just going to be that, b squared minus a squared over 2 by finding the area of a trapezoid, right? We did that, no big deal. But then we went through the process of actually doing the limit of the Riemann sum. And you can watch this if you want to see the whole thing. It's on my YouTube channel. And what we found when we actually went through the process of finding the limit of this Riemann sum, and notice that we haven't specified the limits here, it's just a and b we called it to keep it very general. We got the same answer. We got the answer b squared minus a squared over 2, right? And that's totally general. So then we said, okay, can we think of a way that we could come up with that answer without having to go through the whole process? And how is that related? If we write it in a slightly different form, it becomes more obvious. b squared over 2 minus a squared over 2 can be written in the form x squared over 2 over the limits a to b. Because what this means notationally in math is it's going to mean the value of this expression at b minus the value of that expression at a.
Is there a name for that notation?
Probably, but I don't know what it is. I've never known, so it can't be that important. What does that look like? Well, x squared over 2 is related to our original function, f of x equals x, in the way it's the antiderivative, isn't it? Right? The antiderivative of x to the 1 is x squared over 2 plus c, right? And so what we find here is that we can add up the area under this curve by simply doing what we used to call the antiderivative and evaluating the answer over the interval from a to b, right? The c, where'd the c go? Well,
There you go.
it disappears, right? Because I'm really just going to end up with x squared over 2 evaluated at b is going to be b squared over 2 plus c, right? Minus the value at a would be a squared over 2 plus c. Well, the c's cancel, right? So we don't ever write it because they're always going to cancel, okay? And so we end up with this numerical answer. This is a number now, right? Which represents the area under the curve. Well, how do we denote that process? How is that different from just an antiderivative? Because the answer to the antiderivative would have been the family of curves, x squared over 2 plus c, right? And those would have just, what would that family of curves have looked like? X squared over 2 is just a parabola, right, that's been widened slightly. And when I add c to it, I'm just vertically offsetting them, right? And so the answer to, and this is an important point. Let me just add a page. You know what, I better do this at the end. So this shows up at the end of the, because I'm just kind of tacking this all together as one group of notes. Let's just make this point. So this is the difference. Between an antiderivative which we're going to come to call an indefinite integral. And 2, an area under a curve, which we're now going to call a definite integral. Okay, it's for sure. Well, in the first case, let's just take the example we did. The antiderivative of x dx gives us back x squared over 2 plus c. That is a family of curves. If I were to graph those, it just looks like this. an infinite family of curves, right? And each trajectory is one solution from the general solution, right? Does that make sense? There's an infinite number of solutions encapsulated in this one family, right?
What is that?
What's that?
X squared over 2.
Plus C, that's my crap, plus C.
Okay.
I get so excited, I
Plus
get so excited I can't get,
I thought it was like the summation thing.
no. X squared plus C.
X squared.
Okay, so
Summation what?
what's number 2? The area function is totally different, right? Because we took the example, the integral of x dx from 0 to 2. Is that what we did? No, we did like x squared, didn't we? We did x squared, right? And we found that the answer was not by this process, but the area is represented by this integral. The area was 8/3. It's a number. It actually represents an area, right? They're totally different. What's notationally different about these two? Those things, right? That's what we did, isn't it? We added up the area under the curve x squared from 0 to 2, right?
We had X.
So,
Yesterday, you're right, but remember when we go back, let me go clear back. We'll connect the dots here.
so all that X is just the n value, or?
Yeah, right? We did this, notice here, we added up the area under x squared from 0 to 2, and we got the answer 8/3, right? Well, now we would simply write it this way. We went through that whole process, but it's all summarized in this one elegant little statement here. The definite integral of x squared dx from 0 to 2 is 8/3, right? So what are these things called? Those are called the limits of integration, right? They're telling us when we're doing a definite integral, they're telling us the left and right intervals that encapsulate the area, okay? They look, in terms of the math, right, the actual algebra of calculus, the two processes are essentially identical. You just add this extra step at the end where you're going to evaluate your answer, right? Weird, but they mean totally different things, right?
Well, but those are two different problems, right?
They are. They're two very different
Different
problems.
problems.
Yeah, they're two very different problems because this is telling us an antiderivative, right? And this is telling us an area under the curve.
But
It's just that the
they're-
math gods linked those together for us,
But
which
they're
is
not
handy.
even talking about the same curve, though.
Oh, no, you're right, these
Okay,
are.
good.
Yeah, you're
Okay.
right, these are. So, you're right.
Okay, still got it.
So let's,
Okay.
let's, good point. So how about if we change this one very slightly? What if we say this? Let's say this. Let's change this so at least they're the same integrands. Right?
Now I'm seeing it.
This makes it a lot better.
Okay, yeah.
But it's just two terms.
X cubed over 3 plus C, right? Does that make sense?
Yeah.
Okay? So we get different answers that represent different things, and by the way, this is no longer the right picture, is it? Right? So it should be a family of cube functions, cubic functions. So,
Teaching us lies with.
yeah, I know, always. So these guys are the limits of
So if it was like 2 to 4,
integration. Yeah.
would you have to do 4, or would you have to do 2? Because, well, to get like 8/3, I
Tell you
assume
what,
you needed 2.
let's do
That's
some.
X.
Let's do some
Okay,
problems.
Let's do some.
So this is what we said. Then, did we ever? Oh, I get lost in all the stuff we did. I don't know if we ever actually wrote down.
Calculus.
Oh, here it is. Here's the fundamental theorem of calculus. Okay, right here. So what does this say? All right, this stuff right here. Is the first fundamental theorem of calculus. We just call it the fundamental theorem of calculus. And it just says that the area under the function f of x, right, is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a, which we can summarize using that notation. Okay? And we looked at a couple examples, but we'll do more today, so you're not really behind now at all. Exactly. Okay, so let's try some of this. So let's add up the area. First of all, I want you guys just to write out the integral, right? So just represent this with an integral. But let's add up the area under. Okay, I want you to. You're gonna discover some things here that are just gonna blow your mind. So let's add up the area under the curve. On let's make that, let's go -1 to -4. Negative, yeah, you're right. Should be reversed.
Just be.
Okay, so write out the integral first. So yeah, you got a paper out.
You silly guy. Kobe, cookies. Kobe, cookies. Cupcakes.
How much time we got?
5 minutes.
Oh, good, okay.
5 minutes. That's 5
Yeah,
minutes.
thanks. You want to start playing your juice harp right away.
I only got sick from playing that.
Yeah.
Yeah, you need don't recall walking.
There's no soup.
16, 64.
What's 64 times 4?
That's 128, 256. Math?
So what were you doing?
256, and then you can just divide it by 4, so it's like,
Yeah.
no biggie. Pretty stupid, so.
Being honest.
No, yeah, I know, but if I think I'm smart, then I just get too big.
Sure, that's
That's
how
what-
that differs from one.
You know what? You're not wrong. Then I need to do some.
Okay, so what do we, how do we, before you actually do the math, you can keep going in a second, but how do we write this as a definite integral? What's this look like?
Okay, so, the,
Negative ones,
Negative, actually it should be -4 to -1, right?
So that you put this,
yeah,
the
X.
smallest number above.
Yeah.
Okay.
What goes in, what's the integrand?
X cubed. Del dx.
That's it, right? Okay, so what's the answer?
1 second, I'm almost there. Just
I don't need the numerical answer. What's
X to the 4th.
evaluated from
Negative 4 to negative.
-4 to -1? Okay, so here's the other thing we talked about yesterday, right? We could write this as -1 to the 4th over 4 minus -4 to the 4th over 4. Or we can treat this 1/4 as a constant, right, and pull that out front if we want to. You don't have to do this, but we could write this as 1/4 times x to the 4th evaluated from -4 to -1, right? And so that's just gonna equal what? 1/4 times, what's -1 to the 4th?
Positive
1. What's -4 to the 4th? It's just gonna be 4 squared, right? 16 squared is what?
256.
There you go.
Why is the 1/4 negative?
Yeah, what's negative 1/4?
It's, oh, it's a typo.
Ah.
Just say it right up.
Yes.
Darn it anyway.
It's actually a wrong of Michelle.
I'm on a roll today, I've made a lot of mistakes. Okay, so what's our answer gonna be then? We get, negative 255 over 4,
Yeah.
okay? What?
That's the
What?
point where everybody stops.
It's wrong now, not right now.
No, it's right.
No, you're wrong now.
We're talking about something else. Go
Oh, I got the answer, but then I plugged it back in and I got 4 million. And so, but I still got that number. I got that number on my paper, it's just I didn't do more stuff.
Okay, but what's with the negative sign?
Because it's.
Above, below the
How is
x-axis.
area negative?
Because it's under the X.
It's
Yeah.
imaginary.
It's under the X.
Yeah, it's under the x-axis.
Imaginary area.
Oh, you're back.
No, it's real area.
Have we talked about how imaginary numbers exist yet?
I'm sure if we haven't, we could, we'll take it when we gotta break in the action. Remind me to talk about imaginary right now.
Yeah.
In physics or just in calculus?
No,
So like in 5 minutes?
No, we can't interrupt today.
Oh, shucks.
So what's this look like then? We just had, what do we have, x cubed was our function?
Yes.
So all we've got going here is we're just going from like there to there, right? And so you got it, area under the x-axis is considered to be negative, right? Okay, good. So what's this gonna be then? Try this one, let's have a rate so you can do this one first.
Okay.
So you can do this first. I wanna
Taking an
know
L on this one, guys.
what's the, let's try this, what's the antiderivative of, let's say, x to the 5th dx from negative 5 to positive 5, go. So you can get this first.
Yeah.
Zero.
Okay.
What is it?
Zero.
You're right.
Oh, Jesus Christ, I hate you.
Wow.
Oh, I get that.
That was a trick question.
Okay.
That's a trick question.
No, it was a great question. How'd you-
21.
Trick question. Trick
Okay,
question.
so explain yourself.
Difference of b minus, or a minus b, I'm gonna say whatever, but it equals 0.
It's gonna equal 0, and you don't even have to think about this. You don't
Yeah,
have to
no,
get
just-
bogged down with the calculus, just think about what it represents, right? If you have an odd function, right, an odd function has symmetry about, rotational symmetry about the origin, right? If you have an odd function and you're gonna calculate an area over symmetric limits of integration, you're gonna get as much positive as negative, aren't you? Guaranteed. So that's a theorem in your book, I don't know what it's called. It's,
Okay, but
But if it was
wouldn't you
X
still
to-
need to like figure out the total area? Because like
No.
that's kind of a.
No, you found, now, okay, there's
But like
different,
in real life, if applying this problem.
Okay,
in real life.
let's apply this in real life. We could do this in real life, well, we're not quite to this point in physics yet, but if we wanted to, okay, remind me to apply this in real life in about a week after
Wait,
spring break.
quick.
A week after spring, so
When
2
in
weeks.
physics, we've talked about work and energy.
Can they just leave then for the non-physics people? 'Cause-
No, talk about it in physics.
No, well, and in here, that's
Oh.
fine.
And?
Well, how about if we just talk about it right now, real quick?
Yeah.
So don't give this away in physics.
What about
yet, but
economics? He said economics.
Economics. You could.
Okay, but I mean,
You
in
could.
economics, it makes sense that it would be 0. But I'm talking like, if you have some sort of weird
Are you
weird
calling
shape.
money not real?
You have a weird shape on like a board, okay? And you need to figure out, oh, what's the area of this board that I'm gonna be cutting out this weird x to the 5th
Okay,
sort of line.
but
That's
now-
what I'm thinking.
You see, here's the thing though, you're limiting our use of the word area to geometric area, which in physics we almost never, or in physics or calculus we almost never do. For example,
Come
if
on.
we wanna add up the
At least
area
we found the
under,
limit.
You can take the limit, but you can't give the limit.
if we add up the area under a force displacement graph, that's called work, right? And so what if we wanna add up the area under a force displacement graph, where let's say we've got a spring, that's sliding an object on a frictionless surface back and forth, right? So what's the force gonna be acting on the object? As the spring pushes the object out this way, there's gonna be a displacement. As it pulls it back, there's gonna be a displacement, right? And so we would end up getting something like, if we look at our profile of force versus displacement, it's gonna look like this. It's gonna look like maybe something like that for one oscillation, right? So it's gonna, the spring's gonna, for example, if it's compressed initially, it's gonna apply force in that direction to push the object out, right? And then once it gets past the rest state of the spring, it's going to pull it in the other direction as the displacement increases. So the force is gonna change directions, right? Okay, so what's the area under that curve? When it gets to the other side and it's come to rest again? The answer is, it's 0.
Yeah.
And it is 0, because as we'll learn in physics, the amount of work done on the object is it's gonna equal its change in energy, and the energy hasn't changed. It was given some work, right here it was. At this point it had done some work, because now it had accelerated the object, and so it's got some kinetic energy. But at the end, it's coming back to rest, And so it's lost that kinetic energy, and it's remained on a level surface, and so it hasn't gained any gravitational potential energy, and so there's no net change in energy, right?
Wait, so if
And
we're-
so that you'd get as much positive and negative, and the net work would be zero.
So if we're doing energy, like we're measuring
So-
energy,
Yeah.
but if we're doing energy and you only do it from the interval where it's above the graph, energy is the area of that curve.
Yeah,
In joules.
exactly. How cool is that?
How are you gonna teach that in physics?
I'm not gonna teach it with calculus, but this is what it means in calculus.
Good luck.
Yeah, yeah. It makes it, honestly, it makes it harder to teach. See ya. You bet, any day. So it makes it harder to teach without calculus in a way, because you have to, it really does, you have to
With
sort
all
of
like
contrive
the,
things.
not algebra, but the like acceleration and then velocity and all that stuff, that honestly calculus helps so much with like visualizing.
Yeah, it does,
all
yeah,
different things.
it does. They really should be taught together, that would be best. That's how, in a past life, that's how I taught it.
Who's that guy that was here?
Yeah. Was he
Oh,
like
he's
a
just a
surveyor?
teacher, he's just a teacher.
Oh, is it?
Yeah.
Oh, yeah. There was like IT for
Yeah, that's
college
what,
or
yeah, I
something.
thought he was IT, yeah. I didn't know he was a teacher.
Yeah, no, he's Mr. Griggs, he teaches down the hall, but he just wanted to come back and review some calculus.
What's he teach?
He teaches like, algebra one,
Oh,
I think,
okay.
and
Algebra 1.5.
something like that, I mean, yeah. Does that make sense though?
Yeah.
Okay, so I got another one for you. Let's have a race.
Will
This
be a
one you have to
real
do a
one?
little bit of work on. This one
Okay.
you have to do a little bit of work on.
It'll be some bulk.
Okay, so, but it makes a really good point. Makes a really good point. So we could summarize, real quick, we could summarize that last one. In general, we could say for f of x, when f of x is odd, it's an odd function, then this is true, right? The integral of f of x dx from negative a to positive a is what? Zero. Okay, you get that? Okay, let's try another one. Let's have a race.
I'm not gonna write it.
What's the area under the curve x squared from negative 3 to positive 3?
2x. I actually know what it is, but I can't do that fast, just.
No.
Is it 1?
What are we out of here?
15.
Is
15,
it
okay.
2?
Negative 54.
Is it 1?
No, it's gonna be positive.
No.
It's 1.
But don't you need to do negative 3 times minus the
I,
positive, right?
No, it's 3 minus negative.
Oh, it's
Yeah.
3 minus,
Yes,
oh.
it's the upper limit minus the lower limit.
18.
Oh, so it's
18.
54, so it's positive 54.
Positive 54, okay.
Okay.
So here's how we could get that then, right? There's two ways, but I want to show you the shortcut. This next one is really just a shortcut. But this is just x cubed over 3 evaluated from negative 3 to 3, right?
Yeah.
Which gives us 3 cubed over 3 minus negative 3 cubed over 3, which is 27 thirds, which is just 9, isn't it? Minus negative 9, so I get 18. Okay? But watch this. Think about what this looks like as an area. This is an even function, right? So if it's an even function,
Symmetrical across the bat.
exactly, it's symmetrical, it has folding symmetry about the y-axis, and so let's just say that's A, and that's negative A. What do you know about those two areas?
Equal.
They're equal. And so I could say then, in general, I could say that for an even function, the integral of f of x dx from negative a to a is just 2 times the integral from 0 to a, right?
Where'd you get negative 54?
I forgot the 3 on the bottom. That was my bad.
Why'd
Right,
you
it
confirm
was
it then,
18.
Julia?
Okay, why is that? Oh, I
I said 18.
54, yeah, so, okay.
I just assumed she
I
was
know.
right. I wasn't doing
I was doing it
it.
in my mind, so I forgot the 3 on the
She
bottom.
doesn't have her
That was
left
my
arm,
bad.
she's handicapped.
Okay.
Actually, literally.
So how does this help us? How does this help us then, right? So this would make, this helps us a little bit, because if I can put a 2 out front and make that a 0, look how much easier this integral is to, this integrand is to evaluate. I end up with, or antiderivative is to evaluate. So we end up with 2 times x cubed over 3, so just call it 2/3 x cubed evaluated from 0 to 3. Well, what's it going to be at 0? 0, right? And so this is really just going to be 2/3 times 27. See what I'm saying? A lot easier, isn't it? Right? Now, it's not always going to be that 0, that the area is 0 at 0, but yeah, it is actually. It really is. I think it's,
How could it not be 0?
yeah,
That's a good question.
the value of the function. No, that's not true, because it's really just all we're looking at is the value of the function. And so
Because if the
it
starting
won't
value-
always be, but it usually will be. It usually will be, and it's going to be almost always somewhat easier to use this shortcut.
What
Okay.
happens when it's not 0, when it doesn't equal 0?
Well, I'm just thinking, like, it could be, what if you had, for example, the quantity x plus 3 was your, see, it's hard for me to talk about this because we haven't done some stuff that you guys, when we have done a couple things, think of it as like the equivalent of the chain rule for integrals, right? When we add that in there, then you'll be able to see pretty easily how it couldn't be, it could be non-zero, okay? Yeah. All right, so let's throw in one more thing, because, you know, doing the second fundamental theorem, just taking definite integrals is not very hard. You guys will be able to do that no problem, right? But there's one other thing that's pretty cool here. This is called the mean value theorem for integrals. Okay, so all this says is, and this is really cool. I want to show you this with a picture.
We got
'cause
4
this is-
minutes.
I can do it in 4 minutes.
Okay.
So this invokes the use of an interesting two-dimensional power tool that I want to introduce you to. It's called my calculus grinder. So if we go from A to B, and we've got some area that looks like that, right? And I want to know what the average value of the function is on that integral. Well, what's the most probably meaningful way for me to do that? Here's what it is. Would you agree that if I were to contain this area, let's say I'm going to extend these walls infinitely high, don't really need to put them infinitely high, but then I'm going to bring in my two-dimensional calculus grinder and I'm going to grind down this function, and the rubble that's created is just going to, it's frictionless, so it's just going to tumble down the slope, and it's going to tumble down the slope and eventually form a rectangle, right? So what's that rectangle going to look like? Well, it's going to look something like that, let's say, right? Wouldn't the height of that rectangle really be the most, you know, intuitive and useful definition of the average value of the function?
It's the trapezoid thing again, basically.
Oh, I see what
Well,
you're saying. So
this would actually be a rectangle, right?
Yeah.
But no, it's like with the trapezoid, you take the corner, you make a rectangle.
Exactly, right, it's the same idea, only in
No,
this
but-
case, it's even more useful because this was a curve previously, which doesn't have a geometric area,
I
right?
figured it out. So all you need to do is just find out the area underneath, which we know how to do.
Yep.
And then you
Divide by-
that by the area, the distance between the two.
That's it.
Because then you have
Exactly.
the length, and then that's the height, and then that's that.
That's it, so that's the average value of the function, right? It's just gonna be the area under the curve divided by its width, right? Because that's what gives you the height of the rectangle, isn't it? See what I'm saying?
Oh, that's nifty.
That's pretty useful, right? Yeah, that's pretty useful, right? Okay.
That's swanky.
He's got that pretty quick, that's good. So then we could define, if we define C as the place where the function has its average value, this is how we say average value in calculus. We would say that f of C is just equal to the area under the curve, f of x dx, from A to B, divided by B minus A, right? We good? Okay. Man, that's a lot of math packed into 45 minutes.